Okay, good afternoon, everyone. So today we are looking into gravitational waves, the linearized theory of gravitational waves. We are going to make a very basic assumption, which is that the metric is a little different from the Minkowski metric. In other words, in the linearized theory, we will have to raise or lower indices using this metric. That's what we are going to be using instead of this. And of course, you can see, as will be expected from any metric tensor, this relationship is also applicable. Just as we know, if we replace these two etas with g's, we will still obtain this conical delta. Some try to give this this expression as this plus some epsilon h mu nu, where they assume that this is something also, this is also considered to be far less than 1, just like the modulus of this perturbing term, if we can call it that, is also far less than 1. But this is all superfluous or redundant, if you like, because we can do without this in our formulation. And you will see just very soon, as long as, of course, we assume that every such term as product. So we are going to be doing every analysis here with this in first order, not in second order. So every such term as this, for instance, rho, or maybe mu nu, and then h mu rho, but comma some sigma, or even a product of h mu nu, comma, let me say rho, h alpha beta, just for the sake of argument, comma sigma. So, or even maybe h mu nu and h mu rho. Yeah, exactly. Okay, that's what I wrote first. So when we have a product of this and itself, and its derivative, or the product of two derivatives of h, then any of this combination can be considered to be second order in h. It will be considered to be of second order in h. And all such terms we are going to be discarding or set equal to 0. So like I've said, you may find some in some literature or some books that I've seen them include this also. But you will see that we will do just fine without it. So let's get started. For the first time, okay, so maybe it will be nice to see really that this does indeed follow from that. And of course, it's what we know. So in general, we know that g mu nu, g, so I can say nu k, is the same thing here as the conical delta of k mu. So in other words, so let me do this around this place. So in other words, conical delta k mu is the same thing as, okay, so I'm going to make an assumption here with an expression that I'm yet to prove, but maybe I'll do that soon. So I will, you should know that the metric tensor, the inverse metric tensor, has instead a relation of this kind. So instead of eta sub mu nu plus h mu nu, we have eta, of course, contravariant indices minus h mu nu in this case. So I'm going to take the product of the two, and I will be assuming this for this. So that's why I just postponed. So now I'm going to say eta mu nu plus h mu nu, and then here I have with me eta nu k plus minus. So that's, like I've said, minus h nu k. Now this is going to give me eta nu mu, eta nu k minus mu nu h nu k plus here h mu nu eta nu k, then minus, I have a product here of h and then nu k, and then of course, like I've said, this is of order h squared. I will discard that. Now here in this case, I'm going to have, like I've said, this is what we intend to show, nu k. Now if I were to lower this, so I would necessarily will have to lower, so minus h k, here I'm going to have mu by lowering this nu, plus here I'm going to have h, I'll be raising this nu, so this is going to give me kappa mu. Of course these two cancel, and then I'm left with eta mu nu, eta nu kappa equal to Dirac delta, conical delta, kappa mu. Now one other thing you have to know, just as the metric tensor is symmetric, h also is symmetric. Mu nu mu. Of course, the same thing is applicable to our Minkowski metric. Of course, being a metric, it has to be symmetric in its two indices. So that is one property we can at least rely on right now. Now, looking at the next expression there that we've written on the left-hand side, which was this that we have used now without actually proving. Okay, so we have been given a direction here first. The Minkowski metric, like we have been told, of course, is a diagonal matrix written in this form, and is a constant. Differentiating it with respect to any coordinate gives you 0. And like we've stated, this expression is just to say, in this linearized theory, we will necessarily have to raise or lower indices using this Minkowski metric. That is what we will always have to do in the linearized theory. Unless, of course, you're working with a real tensor and not the linearized tensor. So, for instance, in this expression, we are going to find the linearized Riemann tensor, the linearized Ricci tensor, linearized Bianchi identities, linearized field, Essen field equation, and hopefully linearize a lot of things. And in all these linearized objects, we will have to raise or lower indices using this. But for any tensor that is exact in its right, and no such approximation applied to it like this, then our raising and lowering of indices will, of course, be effected using the conventional or what we know to be the metric tensor. Now, in this case, in trying to show this expression, we are going to be using this. We are going to assume, for instance, okay, we are going to feign ignorance, not knowing what is happening, but we are here including a factor A, thinking or maybe believing that that will be able to give us what it should be. First of all, using again the same kind of analysis we've just used now, G mu nu. Okay, I can use nu k here. This again should give me a conical delta of mu kappa. Okay, now here at this point in time, we have what this should be, of course, G nu k. So let me not rewrite that. But G nu k, following this expression here, G nu k in this case will be eta nu k. And since it's covariant, this will be plus H nu k. But then this contravariant, we are here assuming that this will be eta nu, but plus A mu nu. And note that we are trying to, so here I'm not assuming it's minus because I'm actually trying to show that this A should actually be minus, because then only then will this expression look like this. So that's just the essence of all this. So we are assuming again that this should give us that. So by this product or expansion, this will give us that plus A eta nu k H mu nu plus H nu k eta mu nu plus A H nu k H mu nu. All this is equal to the conical delta. Again, of course, here we have a product. This is of order h squared, so we discard that term. What are we left with here? We're left with here, this, we are going to make the result of what we had before. Yeah, we're going to make use of this result, which was what we proved previously. So this is going to give us a conical delta of nu kappa. And here I'm going to have here with me some plus A eta nu kappa multiplied by H mu nu, and then plus some H nu kappa eta mu nu, and this is equal to the conical delta mu mu kappa. Sorry, did I make a mistake here with something? This and this is to give me mu kappa. Okay, so what I used here was nu kappa, here mu nu. So I'm expecting that this product here is to give me, so the conical delta here, because what I have repeated is nu, and this should be mu, not nu, please. This should be mu. And of course, this is the same with that. And we can see being on opposite sides of the equality sign, they cancel, and we're left with here A eta nu kappa H mu nu to be equal to minus H nu kappa eta mu nu. Okay, now what do we do next? Now looking at this expression, we have this to be equal to that. all this, what it looks like is just like we have this particular indices here moved over here and that coming over here. I'm looking at it carefully. Well, let's just work on this term here. H nu kappa eta mu nu is the same thing as, supposing I decide to do something like this. H, let me say alpha beta, with the idea that I have some eta here, like I said. So what I'm doing is trying to raise these two indices. I'm going to say eta nu. So this particular one here is raising, yeah, exactly. So I will be sort of using this particular metric. If I were to lower this alpha, I will be back here. So, and then this, for instance, should give me the same thing as beta, and then here I can use kappa. Of course, we know that this is still here, mu nu. In other words, we are saying that this should be the same thing as that. Yeah, that is true. So, if we were to sort of evaluate or lower this alpha and beta, we're back here. Now, but then you can see that I can try to combine these two metrics because this and this are the same. So this is going to give me a chronicle delta of mu alpha. So this is same thing as H alpha beta, chronicle delta of mu, and then alpha, eta here, beta kappa. And now that should be the same. So this is going to give me H. Okay, let me see. If I try to evaluate or make use of this chronicle delta, this will give me here mu, beta, and then that will give me eta. I don't have alpha anywhere else, so I have here beta kappa. Or you can say, well, it's symmetric, like we've said, mu beta. So what else do we do? This is something that we started with from here. We started working with this from this place. I can decide to make beta, being a dummy index, I can decide to make it equal to mu. Okay, so I think nu. I can change it to nu, and then this will become eta kappa nu, not mu, kappa nu, h mu nu. Now you can see that I have just shown you here that h, let me write this somewhere on top because, so I've just shown here that h nu kappa eta mu nu is the same thing as eta mu nu h, that is not mu nu, please, that is kappa nu. I am not, so this is h kappa nu and here h mu nu. Yeah. Now you can see, so maybe this should be boxed. This is a really very interesting expression. So it's just like saying you kind of move this directly to this side and move this directly to that side. That's what we've done here. Or if you like, you can write this h first, mu nu, eta, this. Then it will look like what I'm saying. So it's like you move these two indices onto the h and these two down onto the eta. So this is a property. Of course, be careful. We have just made some approximations that led to this. This is not applicable when this eta is replaced with the metric tensor or G. So this approximation is all for the case for which we've made these approximations. Well, what is the essence of all this? Remember here we had an expression, so I could say that this is minus of h mu nu, eta here, kappa nu. Now, but look, take a look at this. This last factor here is the same as this one. So in other words, so I will take that on top. In other words, we have just shown that a eta nu kappa h mu nu is the same thing as minus eta, the same eta kappa nu, well, which is the same h mu nu. So this is the same with that. This then implies that a is equal to minus 1. So we have been able to illustrate what we're trying to say, showing that for the inverse metric tensor, this is what is applicable for the approximation we're making in the linearized theory of gravitational waves. Okay, now, so that's it for the two metric tensors. the metric tensor and the inverse metric tensor. Now, looking here at the affine connector of the Christoffel symbol, we would like to write this in this linearized form too. So very quickly, I'm erasing everything we've just done. Now we had here for us, so maybe I should write that all over again, sigma, and here I believe is lambda mu equal to 1/2 g nu sigma mu, comma here, lambda plus g lambda nu, and then comma, here I have with me mu minus g mu lambda comma nu. Yeah. Okay, so having written this already, now what are we going to do next? First of all, let me look at this, each and every one of these factors in individually. G mu nu comma lambda is the same thing as the g mu nu dx lambda. Well, g mu nu in our linearized theory, so we can see the s lambda here of, so what we're expecting is eta mu nu plus h mu nu. Of course, we've stated that this is a constant. We've in fact written that as one of our tools right from the beginning here on this side of the board. This derivative is 0. So essentially, this is something as just the h mu nu dx lambda. In essence, g mu nu lambda is something as h mu nu lambda. Okay, so well, that may be confusing. You may just think that this is the same thing as the kind of linearized form of the metric tensor. Well, now just remember that this is actually the perturbation, or what we're using yes to cause the change. We're saying the metric tensor should be a little different from the metric tensor. So that's what it is. So the only reason why it looks like that is because this is the derivative. Otherwise, if h were to be very small, g mu nu will in fact be equal to eta mu nu and not h mu nu. Well, this means in turn that g lambda nu comma mu is just the same thing as h lambda nu comma mu, and g mu lambda comma nu is the same thing as h mu lambda comma nu. So that's what all these factors in there are doing for us. Now g nu sigma is the same thing like we've said, nu sigma minus h here, nu sigma. So if I were to substitute this, lambda mu, this is the same thing as 1/2 eta nu sigma minus h nu sigma, and then in here I will simply have h mu nu comma lambda plus h lambda nu comma mu minus h mu lambda comma nu. That's what I will have. Now you can see from this second term, yes, of course, you can see that this will be multiplied, or when multiplied with each and every one of these terms, will give us something of second order. So this is h lambda. So this is the same thing as h in second order. So every such term that comes with this multiplying that for us will be discarded. So we are going to have that the linearized form of the affine connector or the Christoffel symbol is simply this: h mu nu comma lambda plus h lambda nu comma mu minus h mu lambda comma nu. So this again should be boxed. As you can see, this is the linearized form of the affine connector. So we've had maybe about 3 results now, we should say. This one comes with the assumption of the theory, but maybe we have been able to write this affine connector in the linearized form. Now we're going to try to do that now for the Rayman tensor. Okay, very quickly. The Rayman tensor lambda here is mu nu k, or kappa. This is gamma lambda and mu nu comma kappa minus lambda here, mu kappa comma nu, and then plus eta mu nu and gamma lambda kappa eta. Oh no, this should be lambda, sorry. That is lambda. I think I'll have to make that quite apparent. That should be lambda minus, I have here with me eta, mu, kappa, and gamma. Yes, the first here should be lambda, nu, eta. Okay. Now this again we want to write in this linearized form. So basically, first of all, let's just try to look at these two terms. First of all, gamma eta, or should I say gamma, eta mu nu is multiplied with this kappa lambda kappa eta. Now, so if I were to use, I've just erased my, what is it called? But if I remember correctly, what we had actually was eta sigma. This was for lambda mu. What we had was 1 over 2 eta nu sigma. So if I remember correctly, so yeah, that's what it should be. Comma lambda minus g here, lambda nu comma mu minus g mu lambda comma here nu. So I would expect that gamma eta mu nu will be some half eta here. So I have here some sigma and the dummy index. So this eta comes along for the right. Eta on top. Well, it doesn't matter. I'm going to use sigma this time around as my dummy index. Now this is h. In this case, I have with me one of those. So this is h exactly. So the dummy index that we chose was mu. I'm choosing here sigma. And the first one, of course, which is on top, is nu. And this is eta. And it's being differentiated with what I know to be the first. So please, we're going to be able to write this out correctly. So what we are using as a dummy index, I'm going to use alpha as my dummy index. Eta here is supposed to follow me. I'm going to use alpha as my dummy index. H, in this case, one of those indices is mu, and the dummy index comes along. So one of these indices here, so let me use mu, which is the first one, and the dummy index comes along, which is alpha, comma, the second one, which is nu. Then plus h, again, one of those indices that we have here is going to be nu, just like we had lambda here, and the dummy index nu that comes along, so this is alpha, then comma the first one, which is mu, right? But then minus, so this will be h. Oh, no. Sorry, please, I just made a mistake with this. Remember, this was supposed to have been h, not g's. Okay. Yeah, so that is taken. So the two indices here, really, mu, nu, comma here, what should have been the dummy index this time around coming along for the right, that. And that is what it should be. Again, because sigma never occurred, so our eta never occurred anyway. Well, that is one way of putting this. Well, again, so well, for the sake of argument, let me write is lambda k eta. So this is going to be 1 over 2. Eta, this is lambda, some beta. So I'm going to have some h, k, beta, comma, eta. H, eta, beta, comma, here, kappa, minus h, kappa, eta, comma, beta. So this is what I expect for the 2. So in evaluating the linearized form of the Rayman tensor, I will have to deal with such terms as this. The product of the 2, which we have here already, eta, mu nu, and gamma here, lambda k eta, or kappa eta. Now in the product of these two, I'm going to have some 1 over 4, eta, alpha, eta here, lambda beta, and then I have the product of all this. Yeah, done. Now you can see that in the end, this whole product, this is a term, or yeah, containing all some h, derivatives of h though. Now the same thing here, derivatives of h. So it is clear that from all this, all we are going to get is some combinations as this, nu, and maybe some that, beta. So for each term we are going to obtain in this expansion, we are going to have such things that are second order in h squared. So for that, this is 0. Of course, if I had maintained some epsilon, like I've said, is contained, which is superfluous. You don't need that. That is quite sufficient really to have an epsilon here. I'll get some epsilon squared. So on that note, I'll say because of the epsilon squared, this whole term is 0. Well, you can see that we are doing just fine without any more addendum to this whole formality. So on that note, we can see that this term here is 0, and of course, the same will be applicable for that. So what we are left with for the linearized form of the Rayman tensor will be that k equal to gamma here, lambda, mu nu, comma, k minus gamma here, lambda, mu kappa, comma, nu. So this here, okay, this is succinct, if I'm to say, but in the linearized theory, since we have shown that to be 0, we are saying that in linearized theory, lambda, mu, nu, k, the Rayman tensor should be that. I'm going to make the linearity more apparent by being explicit with my expression for the Christoffel symbol. Now, in this case here, we have such a term as that. Well, it is clear that if I were to write this for lambda, all I have to do is to change this eta here for lambda. This is lambda, and this is lambda, and that will give me the gamma mu nu lambda. And what about the one from UK? Well, it looks like I'm not necessarily unfortunate. I just need to make changes here. So the same lambda and kappa. So I'm going to change eta to mu wherever I see eta. Eta becomes mu. And if that is the case, this is mu. This is mu. I'm guessing this is mu. And this is mu. Of course, we are right with this. So in other words, these two expressions are what we are going to be, or what we are going to need in making the linearity in the Rayman tensor apparent. Now with this expression, this of course will be the linearized Christoffel symbols or affine connector. This will be what we will substitute in the Rayman tensor to give us the linearized Rayman tensor. So these expressions are what we need in this one here to obtain that. So let's just do that very quickly. What we'll have to do first of all is to differentiate. So maybe the first term there is going to be lambda mu nu, comma, kappa. Now that will mean me differentiating this whole expression with respect to x kappa. Well, if I were to do that, I have sort of two factors here, this and that. But remembering that this is a constant, differentiating this with respect to s kappa will be 0. So this might as well be written as this, lambda alpha, but h mu alpha comma nu plus h nu alpha comma mu minus h mu nu comma alpha, but then comma kappa. And then the same goes to this mu kappa lambda comma nu. Yeah, so well, I've got mu kappa here, but kappa mu, of course, we know is symmetric for the Christoffel symbol. So the same thing here is applicable. Lambda beta, but I'm differentiating with respect to x mu, so this is going to be h kappa beta comma mu plus h mu beta comma kappa minus h kappa mu comma beta, and this is differentiated with respect to s nu. Like we said, remember we were actually supposed to differentiate the whole thing here with respect to x nu, which is what we should have done. But then again, because the Minkowski metric, which is what we have here, is constant, differentiating it with respect to x nu will be 0. So that is why we are keeping them both constants in these expressions. So what do we do next? We simply substitute them back into this expression. And this first one here, okay, so maybe I should be again, okay, so I have there to be half. Let me just open up this bracket. H mu alpha comma nu plus eta lambda alpha h here nu alpha comma mu minus lambda alpha h mu nu comma alpha. Yeah. Again, remembering that the whole thing is expressed here with comma kappa. This is not again too much of a big deal, remember, because differentiating all of this with respect to s kappa is 0. So I could take it inside the bracket. Now that will be minusing 1 all over 2 here eta, lambda, beta, h, kappa, beta, comma, mu.